Okay, let's unpack this. Imagine looking out at the night sky, all those stars, the huge stretches of what looks like, well, empty space. What's most of that stuff actually made of? Here's a surprise.
It's probably not solid, liquid, or gas like we're used to.
That's right. Something like 99%, maybe even more, of the visible universe is thought to be in this state called plasma. It's this kind of charged up, really dynamic state of matter that's just everywhere beyond Earth.
And that's exactly what we're diving into today. We've got a whole stack of source material here, articles, research notes, you name it, to really try and understand this often overlooked fourth state of matter.
Yeah, the plan is to get a clear picture.
Yeah.
What is plasma? Where do we find it out there? How does it behave so differently?
Yeah.
And maybe even touch on some, well, bigger ideas about its cosmic role, some conflicting ideas too.
Exactly. We want to give you a shortcut, basically, get you well informed about astrophysical plasma,
Mm.
space plasma, maybe throw in some surprising facts along the way.
Sounds good. It's a fascinating topic. All right, so let's start at the very beginning. Plasma, what is it fundamentally?
Okay, so think of a regular gas. Now, heat it up a lot. Or
Mhm.
expose it to strong fields of radiation. It gets so energetic that the electrons actually get ripped away from their
It's
atoms.
ripped away.
Yeah, so instead of nice neutral atoms, you end up with this soup, this mix of negatively charged electrons floating free and the atoms they left behind, which are now positively charged ions. It's basically an ionized gas.
An ionized gas. Okay. And you said it's not just in like super exotic places like the sun's core.
Nope.
No.
I mean, the sun is a giant ball of plasma, obviously, but you can actually create plasma in, more ordinary ways, too. Energetic particles colliding, strong electric fields, even just certain types of radiation hitting a gas can do it.
Yeah.
But yeah, out in space, it's pretty much the default state for most normal matter.
Wow. Okay. So ionized gas, and there's tons of it. Do scientists kind of categorize it like different types of cosmic plasma?
They often make a distinction, yeah, mostly based on location and context.
Oh,
So when we talk about space plasma, we usually mean the plasma here in our solar system.
our backyard, sort of.
Exactly. The sun itself, the solar wind streaming outwards, the plasma trapped around planets like Earth's ionosphere, its magnetosphere, that's all space plasma.
Gotcha. So astrophysical plasma is everything else.
Pretty much. Plasma outside the solar system. So the really thin stuff between the stars, the interstellar medium, or even thinner stuff between galaxies, the intergalactic medium,
Mm.
or, the extreme plasma near black holes or nebulae.
Yeah.
The fundamental physics is the same. Electrons and ions reacting to fields, but the conditions, density, temperature, scale can be vastly different.
Right. Space plasma, astrophysical plasma. Different neighborhoods, same basic rules. Now, you said it behaves differently from regular gas. This is where it gets really interesting, doesn't it?
It really does. Because it's charged, it's not just particles bouncing off each other locally. One huge thing is collective behavior.
Collective behavior,
Yeah.
meaning,
Meaning a particle doesn't just react to its immediate neighbors. It feels the effects of electric and magnetic fields generated by huge numbers of other charges, potentially very far away. They all sort of respond together, collectively, to these large-scale fields.
so they're all interconnected electromagnetically over large distances.
In a way, yes. But here's a twist. On large scales, plasma is also generally quasi-neutral.
Wait, hang on. How can it be neutral overall if it's made of charged particles that interact over long distances? That sounds contradictory.
Huh. Yeah, it seems like it, right. But it comes down to something called Debye shielding. It's a really key concept. If you were to put, say, a single positive charge into a plasma, a cloud of negatively charged electrons would almost instantly swarm around it.
Oh, okay.
And that cloud effectively cancels out, or screens, the electric field of that positive charge beyond a certain distance, the Debye length. It's like each charge wraps itself in a little fuzzy shield of opposite charges.
Ah, I see. So the electric forces are strong up close, but they get neutralized pretty quickly over distance because of this shielding.
Exactly. And that's actually crucial for understanding why gravity tends to win out on the very largest cosmic scales. Gravity isn't shielded, right? It just keeps adding up. But these strong electric forces in plasma get screened out beyond the Debye length.
Hmm.
So quasi-neutrality holds true for scales much bigger than that length.
Okay, that makes sense. Collective effects happen, but the long-range electrostatic forces get muted. What about those frequencies you mentioned earlier?
Right, there are natural ways plasma likes to oscillate. If you disturb the charge balance, somehow maybe push the electrons aside for a moment, they'll snap back and oscillate around the ions at a characteristic frequency. That's the plasma frequency.
Okay.
And if there's a magnetic field around, which there usually is in space, the charged particles, both electrons and ions, don't move freely. They're forced by the magnetic field, the Lorentz force, to spiral around the magnetic field lines.
Like beads on a wire, almost.
Sort of, yeah. They gyrate around the field lines. And the frequency of that spiraling motion is called the gyrofrequency or cyclotron frequency. It depends on the particle's charge and mass and the strength of the magnetic field.
Speaking of magnetic fields, the sources really hammer home how connected plasma and magnetic fields are. It's like a dance.
It's an incredibly intimate dance, yeah. They constantly influence each other. And the field of physics that tries to describe this large-scale interaction is magnetohydrodynamics, MHD for short.
MHD.
It basically treats the plasma like a conducting fluid and combines fluid dynamics equations with Maxwell's equations for electromagnetism. It's a powerful way to model how plasma flows and carries magnetic fields with it or gets pushed around by them.
And within MHD, there's this idea of the magnetic field being frozen into the plasma.
Exactly, the frozen-in condition. This applies mostly to ideal plasmas, meaning they're extremely good conductors, almost no electrical resistance. In that case, the magnetic field lines get dragged along with the plasma flow. They're stuck or frozen within the moving plasma.
So the plasma moves, the field moves with it, like logs in a river, you said earlier.
Yeah, something like that. But the field lines aren't totally rigid. They can also break and reconnect in spectacular ways.
Magnetic reconnection. That sounds energetic.
Oh, it is. Hugely energetic. It's a fundamental process where magnetic field lines pointing in opposite directions get pushed together, usually at a thin sheet of electric current. They break, and then they snap together with different partners, releasing a massive amount of stored magnetic energy very suddenly.
And that's what powers things like solar flares.
Precisely. Solar flares, coronal mass ejections, these huge eruptions from the sun are powered by magnetic reconnection. Same goes for geomagnetic storms here at Earth. When the solar wind's magnetic field reconnects with Earth's field, it dumps energy into our magnetosphere. It tends to happen where field lines can diffuse or slip through the plasma, where something called the magnetic Reynolds number is low enough.
Wow. Okay, so energy stored in the magnetic field gets converted into heat and particle energy in the plasma. We see this on the sun, near Earth. Where else is all this plasma action happening? You said space plasma is basically everywhere.
It really is. I mean, we already mentioned the sun core, atmosphere, corona. It's all plasma. Then there's the solar wind, that continuous stream of plasma flowing out from the sun, filling the solar system.
Right.
When that wind hits a planet with a magnetic field, like Earth, it carves out a cavity, the magnetosphere, which is itself filled with complex plasma populations.
And the auroras, the northern and southern lights, that's plasma too.
That's the visible result. Solar wind particles get funneled down magnetic field lines into our upper atmosphere, collide with air molecules, and make them glow.
Assume.
And speaking of the atmosphere, Earth has its own plasma layer high up the ionosphere.
Ah, yes, the ionosphere.
And then beyond our solar system, you've got the interstellar medium, the thin plasma between stars, and the even thinner intergalactic medium between galaxies. Plus, things like comets develop plasma tails as they near the sun, and there are even dusty plasmas where charged dust grains are mixed in, like in some planetary rings. It's incredibly varied.
Let's zoom in on the ionosphere for a second. It's relatively close, and the sources gave some detail. How does that form?
Okay, so the ionosphere is this region in Earth's upper atmosphere. Starts maybe 60 kilometers up, goes out to 1,000 or so. It's created mainly by the sun's high-energy light, ultraviolet, and X-rays. This radiation comes in, hits the neutral air molecules, and has enough energy to knock electrons off.
So sunlight literally makes plasma out of our air way up there.
That's exactly it. Cosmic rays chip in a bit too, but it's a constant balancing act. You have ionization happening because of the sun's radiation, but you also have recombination.
Recombination.
That's when a free electron gets captured back by a positive ion, and they become a neutral atom or molecule again. This happens faster where the air is denser, so it's more significant at lower altitudes in the ionosphere.
Okay, so density matters, and I guess the sun's activity must play a big role.
Oh, absolutely. Solar flares can dramatically increase the ionization suddenly, and there's a huge difference between day and night. During the day, the sun's creating plasma. At night, that primary source is gone.
So the plasma starts to disappear.
It starts to recombine, yeah. In the lower layers, where recombination is faster because it involves molecules, the plasma density drops significantly at night. But higher up, In the F region, where it's mostly atomic ions, recombination is much slower, so that layer tends to stick around through the night, although it changes shape.
That explains why scientists talk about different layers, right? The D, E, and F layers.
Exactly. They're basically altitude regions defined by where different wavelengths of solar radiation are absorbed and create peaks in plasma density. The D layer is lowest, formed by things like Lyman alpha UV and harder X-rays. Above that, the E layer, from softer X-rays and more UV. Sometimes you get intense, patchy layers there called sporadic E, and highest is the F layer, from extreme UV, which often splits into F1 and F2 layers during the day.
And these layers, this ionosphere, it's actually really important for us down here, isn't it? Something about radio waves.
Crucial for long-distance radio communication. Different radio frequencies interact with these plasma layers differently. Lower frequencies, like AM radio, can get absorbed by the D layer during the day. Higher frequencies, like shortwave radio, can actually get reflected or bent back down to Earth by the E and especially the F layers.
As they bounce off the ionosphere.
Effectively, yeah. It allows radio signals to travel over the horizon, around the curve of the Earth. That's how you get shortwave radio signals bouncing all the way around the world. The ionosphere's condition, which varies with the sun, really affects radio propagation. And our sources also mention these complex plasma flows within the ionosphere, tying it into the bigger picture of space weather.
It's amazing this invisible layer having such a practical effect. Okay, so how do scientists actually study all this plasma, whether it's near Earth or way out by other stars? Seems hard to get a handle on.
It takes a few different approaches working together. One is in situ measurements. That means sending spacecraft into the plasma.
Like dipping a thermometer in?
Got that, yeah. Instruments on spacecraft like Parker Solar Probe, which flies incredibly close to the sun, or NASA's MMS mission, which studies reconnection near Earth, directly measure the plasma's density, temperature, the speed it's flowing, the magnetic fields, electric fields, right there on the spot.
Getting ground truth, but in space.
Exactly. Then there's remote sensing. That's observing from a distance. We use telescopes on Earth or in space to look at the light, visible, UV, X-ray, or the radio waves that the plasma emits naturally, or how it affects light passing through it.
So looking at it rather than being in it.
Right. And a huge piece of the puzzle is simulations and theory. We use powerful computers to run models based on the fundamental laws of physics. Maxwell's equations for electromagnetism, the Lorentz force acting on particles, fluid dynamics, sometimes even tracking individual particles. These simulations help us understand the processes we observe and predict how plasma will behave.
So observation, direct measurement, and modeling working together. Okay, we've got this picture now. Plasma is this dynamic, charged stuff. It's everywhere. It interacts strongly with magnetic fields, powers things like solar flares, forms the ionosphere. But the sources also brought up some bigger, more contentious ideas about plasma's role in the whole universe, contrasting with the standard picture.
Yes, this is where things get really interesting. Comparing the standard cosmological view with what's often called plasma cosmology, or the plasma universe. Mainstream astrophysics absolutely uses plasma physics all the time. You need it to explain localized energetic things, solar flares, jets shooting out from black holes, supernova remnants expanding into space.
Right, it's essential for that.
But in the standard cosmological model, the big picture, the evolution and structure of the universe, on the largest scales, galaxies, clusters of galaxies. The expansion itself is primarily governed by gravity.
Because of that Dubby shielding we talked about, electric forces get screened out over long distances.
That's a major part of it, yeah. Gravity, although much weaker intrinsically, isn't screened. It just adds up over vast distances. So in the standard view, gravity shapes the cosmic web, pulls galaxies together, while plasma physics explains the more energetic fireworks happening within those structures.
Okay, that's the standard view. But there's this alternative perspective, plasma cosmology.
Right, this is a non-standard view. And its central idea is that electromagnetic forces acting through plasma dynamics play a much more significant, maybe even dominant role in shaping the universe, even on the largest interstellar and intergalactic scales. It's a direct contrast to the gravity-dominated standard model.
And this view has some history, right? People like Hannes Alfvén.
Yes, Hannes Alfvén, who actually won a Nobel Prize for his work on MHD, was a major proponent, along with Oscar Klein. Their Alfvén-Klein cosmology was a specific model within this broader idea.
And how did their model differ from, say, the Big Bang?
Oh, fundamentally. They proposed a universe that was eternal, didn't have a Big Bang origin. They suggested it contained equal amounts of matter and antimatter.
Whoa, antimatter.
Yeah. And the observed expansion wasn't from an initial explosion, but maybe from annihilation processes happening at the boundaries between regions of matter and antimatter plasma, what they call the ambiplasma. Alvin was also really keen on taking physics learned in laboratory plasma experiments and scaling it up to cosmic sizes.
Scaling up lab results. And how did this plasma cosmology idea try to explain things like galaxies forming?
Well, proponents argue that electromagnetic forces are actually more important than gravity when you're talking about the particles moving around in interstellar space. Some models, like simulations done by Anthony Peratt, showed that interacting plasma filaments carrying huge electric currents could naturally pinch and form structures that look remarkably like spiral galaxies.
Without needing dark matter.
That's the claim in some of these models, yes. They propose that these enormous hypothetical currents, sometimes called Birkeland currents, scaled up from what we see near Earth, could explain galaxy rotation curves without invoking dark matter, and maybe even power the intense radiation from active galactic nuclei and quasars without needing supermassive black holes at the center. Just purely electromagnetic plasma phenomena on a vast scale.
Okay, that's a radically different picture. If these ideas exist, why aren't they the mainstream view? Why is plasma cosmology considered non-standard?
That's the crucial question, and the sources we looked at are pretty clear on the reasons. It boils down to a significant mismatch between what plasma cosmology models predict, or fail to predict, and several key, well-established observations about the universe that strongly support the standard Big Bang model.
So the evidence just doesn't fit. What kind of evidence are we talking about?
Probably the biggest one is the cosmic microwave background, the CMB. This faint radiation fills all of space, and in the standard model, it's the leftover heat from the Big Bang itself.
The afterglow.
Exactly. And the CMB isn't perfectly uniform. It has these tiny temperature fluctuations, tiny ripples. Plasma cosmology models have really struggled to explain why the CMB exists at all, why it's so incredibly smooth across the whole sky, isotropic, and especially why it has that specific, detailed pattern of ripples. The standard Big Bang model, with dark matter and dark energy included, predicts that pattern with stunning accuracy.
Okay, so CMB is a big hurdle. What else?
Another major one is Big Bang nucleosynthesis, or BBN. This refers to the creation of the lightest elements, hydrogen, helium, lithium, deuterium, in the first few minutes after the Big Bang. The standard model predicts the relative amounts of these light elements based on the conditions back then, and those predictions match what we observe in the oldest stars and gas clouds incredibly well.
And plasma cosmology.
It doesn't have a similarly successful mechanism. Attempts to create these elements through processes in a plasma universe often fail to match the observed abundances, or they predict that other things should have happened, like producing way more X-rays or gamma rays than we actually see.
Doesn't get the ingredients right, basically.
Basically, yeah. Plus, things like Hubble's law, the observation that distant galaxies are moving away from us and faster the farther away they are, indicating universal expansion wasn't predicted by early models like Alpha and Klein's. And those enormous galaxy-forming electrical currents that some plasma models need. Currents of like 1080 amperes flowing over millions of light years. There's just no observational evidence for currents that huge on cosmic scales. And theoretical arguments suggest they shouldn't be stable.
Okay, so it seems while plasma physics itself is absolutely critical for understanding how things work out there, flares, jets, magnetospheres, the standard model incorporating gravity as the main driver on large scales, plus the Big Bang history, just fits the bulk of the cosmological evidence much better right now.
That's certainly the consensus view reflected in the sources, yes. Plasma physics is an essential part of the astrophysicist's toolkit, no doubt about it. But the specific claims of plasma cosmology about it dominating the large-scale structure and history of the universe haven't been borne out by observations like the CMB and light element abundances.
Right. Okay, let's try and wrap this up then. We've definitely covered a lot of ground on plasma.
We really have. And the big takeaway is just how fundamental it is. Most of the normal stuff we can see out there is plasma, over 99%.
And it's not just hot gas, it's this dynamic, charged state with unique properties that collective behavior, the Debye shielding leading to quasi-neutrality, specific oscillation frequencies.
And that really crucial intimate relationship with magnetic fields. MHD, magnetic fields being frozen in and then snapping loose in magnetic reconnection to power huge events.
We find it everywhere, from the sun and solar wind affecting us here, creating our magnetosphere and ionosphere.
Which is so important for radio waves.
Right, all the way out to the vast spaces between stars and galaxies.
And we looked at the different views on its cosmic importance. While plasma physics is vital for understanding phenomena, the wider cosmological evidence from the CMB, element abundances, and expansion currently points towards gravity being the main architect on the grandest scales, fitting within the Big Bang framework.
It really paints a picture, doesn't it, of science trying to understand the universe across all these scales. You've got the physics of tiny charged particles interacting with fields, and
Sure.
then you've got gravity shaping these immense structures over billions of years.
It's a constantly evolving picture, too. We're always getting new data, refining the models,
Mhm.
which kind of leaves you wondering, doesn't it? Given how much plasma is out there and how complex it is,
Mhm.
what surprising new roles or effects might future observations, maybe from new telescopes or probes, reveal about cosmic plasma? What haven't we figured out yet?